Good day, I'm Dr. T. Welcome to my office. So today I want to talk about mixtures, kind of the next step on our way of moving up from the atom and making things a little bit more complex. So let's talk a little bit about the previous video, and then I'm going to jump into the wonderful world of mixtures. The previous video, I talked very much about atoms and the way we think about different types of compounds. And here, those are what we would call pure substances. So elements would be a pure substance that's made of one type of atom. So it's one chemical made from one type of atom. Diamond, graphite, oxygen. It's the same stuff and there's only one atom. Compounds are going to be one substance, one chemical, but it's made up of multiple different atoms, and they're going to be in a fixed ratio. They're also going to be somehow chemically connected to each other. Table salt, sucrose, a bunch of other things. In this video, I want to jump into the wonderful world of mixtures. Mixtures are going to be where you have two different substances mixed together. Now, here is where I need to bring another concept that we talked about in the last video, and that's this idea that nature isn't really discrete bubbles that we like to think of. Instead, nature is very much a fuzzy Venn diagram. And so I'm going to describe parts of mixtures, but then I want to get into the fuzzy bits of the Venn diagram where things get a little bit weird. So mixture, you've got two or more different substances mixed together. Generally speaking, we don't think of them as being too awfully chemically bonded to each other, although there are definitely some exceptions to that. Very definitively, though, they can be at multiple different ratios, and they're still basically the same thing. You can have salt water, and it could be something like saline, where it's a very dilute. There's a little bit of salt, a lot of water. You could have something like brine, where it's a whole lot of salt and a good amount of water, but there's a whole lot of salt. Or you could be somewhere in the middle with something like seawater. But the idea is you still have salt water in these cases. By the way, side note with the word salt, and I'm going to be using this here in a bit. The English, kind of common everyday English word salt generally means sodium chloride and a couple of derivatives. Whereas in the sciences, a salt is referencing something that could have come from an acid and base and basically is a synonym for an ionic compound, sodium chloride being one of many. Okay, so we've got this idea of varying ratios. Now, you could have a mixture, what we call homogeneous. Homo means same, genius means substance. So homogeneous mixture is going to look like one substance. Salt water is a classic example. Even if you zoom in under a microscope, it looks like one substance, even though you have salt floating around in the water. A heterogeneous mixture, a hetero, different, genius, once again, mixture. These guys, or substance, these guys are going to, if you zoom in enough, you're going to see discrete clumps. Basically, the chemicals are going to kind of clump up. They're not evenly dispersed in the medium. Classic examples would be something like milk. You got the little tiny fat droplets floating around. Spaghetti and meatballs. You got the meatballs, you got the spaghetti, you got the sauce. They're all kind of floating around. And they're definitely clumped up. It's not all homogeneous. It's not like you threw it into the blender kind of thing, which would be disgusting. When we think about that kind of categorization, in reality, it's a bit more of a continuum, and typically speaking, it's a continuum based on particle size. If my materials are little tiny particles, they can easily disperse in each other, and I can make a nice homogeneous mixture. If my particle sizes are larger, though, they're not really going to disperse as well. As such, I'm going to get a heterogeneous mixture. As such, we can start categorizing these mixtures based on particle size, and thus kind of give you a little bit more nuance. Generally speaking, we have solutions, which are going to have very small particles. Salt water is a solution. And then a little bit larger, we're going to have colloids. Colloids are going to be a little bit larger particle size. They're not going to want to settle out typically, so they're going to be fairly stable. And then we can get even larger, we can get into suspensions, and these guys are going to have much larger particles. And quite often, depending on the nature of the suspension, these are going to settle out. There's part of the definition of suspension in some context where it must be an unstable mixture, where gravity will separate out the mixtures if left undisturbed kind of thing. And that's because the particles are even larger in nature. Note, the definitions of some of these words do change depending on context, and this is another reason why you don't want to try and get all lawyery on the terminology, because sometimes the definitions literally change depending on the context they're used. So do be careful with that. Okay, I'm going to jump into a little bit more about the difference between solutions, colloids, and suspensions. But before I do that, I want to jump into a couple of edge cases where the idea of a mixture gets all fuzzy, especially where it starts blending in with the concept of a compound. For starters, definitely implying that a mixture is a mixture of compounds. It could be a mixture of elements. In fact, in theory, it could be a mixture of the same element. So I could have like diamond and graphite powder all mixed together. Let's start with alloys. Alloys are going to be mixtures of metals. So we're going to get metallic bonding. These are incredibly common. Almost all the metals we work with are actually alloys. Very rarely do we work with pure metals. We do occasionally, but usually we don't. And what we're going to do is we're going to take one element, say copper, we're going to add in another metallic element, say zinc, or even sometimes a non-metallic element like carbon. And we're going to mix these together. Now, these are pretty definitively a mixture because you can have a variety of ranges. You may not have any old range, but you can definitely have a variety of ranges. You don't have a fixed ratio of constituents. Sodium chloride, you got one sodium atom for every one chloride atom, well, ion in both cases. Whereas for brass, which is copper and zinc, the ratio of copper and zinc can vary quite wildly. And you'll get a variety of different physical and chemical properties by doing so, as well as you can add in a bunch of other elements into that mix. Now with alloys, when we're doing this, we can talk about substitutional alloys or interstitial alloys, where either I substitute out a atom or where I stick an atom kind of in between the atoms in the lattice. In all cases, I'm going to be modifying the lattice, and that's pretty much exactly what I want to do. By changing the lattice, I change the physical and potentially even chemical properties of my alloy. What makes these a little bit weird, though, for a mixture is that these are part of the lattice system. They're part of the electron sea. So the zinc electrons are involved with the copper electrons. And so they are, by most concepts, chemically bonded to each other. They've got a metallic bond. So it's a little bit unique when we're thinking about mixtures. Usually we're thinking about mixtures of individual chemicals just bumping up against each other, not chemically bonded to each other. Another case where it gets a little bit interesting is that of hydrates. Hydrates are going to be typically ionic compounds, so typically salts, in which water has integrated itself within the crystal structure. Now, this can go a couple of different ways. One, it can literally just be trapped within the lattice, or it can actually get into it. So sometimes it's not necessarily trapped, it actually is like pulled out of the air. We call those hydroscopic. They're kind of cool, but a pain to work with for obvious reasons. So it could be physically trapped in there, or it could actually form chemical bonds in what we call a coordinate complex. And there's actually a whole family of technically compounds, but like barely. Once again, this is the fuzzy side of our definitions, where you have typically a metal ion, and you're going to have a molecule, quite often something like water or ammonia or one of those guys. They'll form a covalent bond with it. These behave very much like a compound with generally fixed numbers, but we generally put these aside because it's definitely a little bit of a different chemistry going on over here. And when we're looking at the hydrates, some of them are very much just physically trapped. Some of them are a hydrate because we're forming coordinate complexes. Put some interesting kind of frameworks where we're blending the concept of compound and mixture together. So there are definitely edge cases. Quite often a lot of books will say you can separate out mixtures using physical means, but compounds have to be separated out by chemical means. This can be a little bit easy to get on the fuzzy side. If I'm talking about coordinate complexes, quite often all I have to do is heat them up. The difference between a hydrate that's not a coordinate complex and one that is can be a little bit harder to tell. Generally speaking, the ones that I can't just bake to drive the water off, odds are those are coordinate complex, but there are ones that are coordinate complex that generally I can heat those up enough and I will drive off the water. But of course, the difference between heating it up and driving off the water is evaporation, and heating it up and driving something off as decomposition reaction is kind of a fine line here, because it's the same basic concept. Additionally, things like alloys, you generally, presumably you could separate them by like heating them up and try and separating them out that way by kind of a classic physical approach. You generally will use more of a chemical approach to separate them out. You try and oxidize one element to get it off, change it to a different chemical so you can separate it. So when we're dealing with these guys, there's a lot of nuance and fuzzy sides to it. The physical versus chemical separation is not a bad way of thinking about it, but it's definitely susceptible to that whole fuzzy layer of the Venn diagram. Okay, now let's jump back into suspensions, solutions, and colloids. I want to talk a little bit more about those. Okay, typically we think of these guys as being a liquid with something dissolved into it. If we've got a solution, it's going to be a homogeneous mixture, and, well, it could be a liquid solvent. The chemical in the majority is the solvent, and then whatever's dissolving into it is the solute. And if that solvent is water, we would call this an aqueous solution. Now, they may just float around freely. The solute may actually break apart if you put an ionic compound in water, and if it does break apart, not all of them will, not all of them are soluble, but if it does break apart, you actually break apart the cations and the anions separately, and they're surrounded by water molecules in what we call a sphere of hydration. And this will actually allow you to conduct electricity. The ions can go in different directions and conduct electricity. We call those electrolytes. But other compounds won't do this. If you dissolve things like sucrose, or generally molecules, not ionic compounds, in water, they don't break apart. You get a sphere of hydration, but it doesn't split into ions. And so we call these nonelectrolytes. And of course, there are molecules that do break apart, something like acetic acid, where it's not an ionic compound, but it behaves like one. So there is some nuance here. So that's normally what we think about when we think of solutions. But water isn't the only possible solvent. In fact, you could really change things up. Air is a solution. Think about it. Just pause for a second. What's the solvent in air? You know the answer. What's the solvent in air? The nitrogen. If you think about air, it's mostly nitrogen with a little bit of oxygen. Well, okay, a pretty good amount of oxygen, a little bit of other stuff. Well, that's 70-some-odd% nitrogen. That's your solvent. And the oxygen would be the solute. It's dissolved into the nitrogen. So we've got ourselves a solution. It's a gas in a gas. We can totally do that. In fact, we can basically do about any pairing we want, almost any pairing we want, and get ourselves a nice solution. So if we want to do a solid and a solid, hey, remember those alloys? Yeah, zinc's a solid, copper's a solid. We're breaking those down into their individual atoms. We're mixing them up really good. Brass very much looks like one thing. You can get some grain structure, but that's more of just irregularities in the crystal lattice. Yeah, alloys are generally going to be solutions. We can dissolve a liquid into a solid. Remember the hydrates? That's a good way of thinking about them. They're a solution with a liquid inside the solid. And there's actually another family of hydrates where kind of the opposite, where instead of water being the solute, being trapped inside a lattice, the water's got the lattice. If it's a ice, so if it's frozen, you have another family of hydrates which are actually ice with things trapped into them. The one that gets kind of the most press is going to be methane hydrate, where the methane molecules are trapped within ice crystals. It gets the press because that's a fairly potent greenhouse gas, or methane is a fairly potent greenhouse gas, and so as this ice thaws, it releases that into the atmosphere. And, you know, we can have a liquid solvent with a solid solute, seawater, classic example. Sodium chloride in its pure form under normal temperatures is going to be a solid. By the way, not all ionic compounds are solids. There are room temperature ionic liquids. They're not very common, but they definitely do exist. Likewise, we could mix two different liquids together. Gasoline is a quintessential example of this. You've got a whole multitude of petrochemicals that are going together. They're almost all in their pure form at room temperature and standard atmospheric pressure, you know, what you would experience on a day-to-day basis, a liquid. By the way, there should be no water in your gasoline. There's probably a tiny amount. There really shouldn't be much. That's not good for your car. So not all liquid solutions have water in them, just kind of to make a point. And you can dissolve gas in water. Think seltzer water or oxygen in the ocean. You know, the fish have to breathe something. And you can have gas as a solvent. Generally speaking, you're really going to have a gas and gas mixture. If you try and do gas with a liquid or a solid, you're not really going to have a solution. But you might have a colloid. So if I want to go for a colloid, this is going to be a little bit larger. They're usually between a 1 nanometer to 1 micrometer in size. So the particles for solutions usually under a nanometer in size. So we're talking atom-sized. So colloids, these are going to be larger. You might get large molecules like proteins, or you're going to get like little droplets or little granules going on. And once again, just about any pairing you want, except for gas-gas. If you put two gases together, you're getting a solution, because the particles to be a gas have to be fairly small. But I can put a solid in a solid, and I can get what's called a solid sol. This would be something like pearl or opal. I could put a liquid in a solid. By the way, at this point, the thing we're putting it into, we don't call it a solvent anymore because it's not a solution. We're going to call it a dispersant. I could put a liquid into a solid dispersant, and we get a gel. Think cheese. Or we could put a gas into the solid dispersant, and we're going to get a solid foam. Think something like styrofoam, although that might be blending a little bit into the next category of suspensions. Liquid dispersions, we could do a sol, such as paint. So a solid in a liquid dispersant is going to be a sol. Think paint. We could do a liquid in a liquid. That gives you an emulsion. Think mayonnaise or milk. A gas in a liquid dispersant. Think whipped cream. That would be a foam, by the way. Solid in a gas. Hey, we can have a solid aerosol. So think about smoke. Smoke's actually going to be one of those interesting ones because it's also going to be a suspension as well. We can do a liquid in a gas. That's going to be an aerosol, so think fog. And gas is not really going to be too much of a thing here, just because it's going to turn into a solution pretty much no matter what you want to do. Now, when you get into suspensions, this one gets a little bit more nuanced with this one. There are some arguments that you can't have a solid suspension. There are other arguments that you can. So suspension, generally speaking, is going to be particles over 1 micrometer. And depending on how you're defining it, they may have to be very unstable. And so if I do a solid in a solid, it's probably not going to be unstable. Or if I have a solid dispersant, it's probably going to be fairly stable. So I might have an aggregate or a congruent, where basically I've got a couple of different solids that are all smooshed together. So you might want to consider that a suspension or not, because it's not going to be inherently unstable. It's not going to fall apart kind of on its own. Likewise, we could have some form of foam, either like a wet sponge or a dry sponge, where we have a liquid in the solid. Once again, not inherently unstable. So some places don't categorize that as a suspension. The quintessential suspension, though, is a solid in a liquid. Think muddy water. And usually that's just called suspension. Once again, we could do a liquid in a liquid. I could not find specific names for some of these, by the way. So I'm not for sure if I didn't know where to look or if these are ones that are kind of weird enough there's no real names for it. But you could do a liquid in a liquid. Think Italian dressing. You know, the one you have to shake up. You got to shake the bottle to get that going. That's not an emulsion. Emulsion is stable. You might call it an unstable emulsion, but we usually just think of that as a suspension. And you could do a gas in a liquid, foam. This would be another case where we would call this a foam, but this would be an unstable foam. So if you think like a root beer, root beer float, how it gets all fizzy on top, that would be a foam. You've got a gas trapped in a liquid. As far as gases go, we could do, once again, a solid in a gas. This one would also be something like smoke. You might want to start calling this an aerosol, probably not. If you think about smoke, it's got different particle sizes, and sometimes you actually want to get into like how big are the particles, because that can be a fairly big deal. So if you want a higher resolution, you may have to go for that. But once your particles get large enough, they settle out. And so if you're close to a fire, you're going to get that like heavy soot. And then as you get farther and farther away, they don't really settle out. They just kind of disperse. Obviously, if you're inhaling that, that's going to be rough on your lungs, and particle size and particle pollution has definitely been a point of recent interest. You could put a liquid in a gas dispersant thing like a spray or a mist. Once again, I was not able to get a good description. And then a gas in a gas, once again, is going to be a solution pretty much no matter what you do with it. So you can have a whole bunch of different mixtures. We'd like to think of solid in liquid. That is like all the examples. It's basically all seawater is the examples. But that's by no means the only thing. Okay, so let's talk about factors that affect the concentration of stuff you can get in your solution. Basically, how much solute can you cram into your solvent kind of thing. And so first, kind of the terminology we're going to use ratios for our units. As chemists, we love molarity, that's moles. So remember how we can count how many atoms or molecules we have using Avogadro's number. Well, we like doing that. So we can do moles and then divide that by liters of solution. That's one of, as chemists, our favorite. It's not the only one. We've got a whole multitude of units. Typically what you will see often, though, are percents. So you'll have, the amount of solute divided by the amount of solution times 100% kind of thing. Now I will caveat, if you're using percents, this is one of the insidious ones. When I say amounts, those were fairly vague things. I could do grams per gram, and we call that a weight per weight percentage. I could do grams of solute per milliliter of solution. That's a weight per volume ratio, or weight per volume percent. I could do milliliters of solute per milliliter of solution times 100%. That's a volume per volume. I could do moles of solute divided by moles of solution. That would be a mole per mole percent. And those would all be different. So assuming the density isn't all like 1, these are going to give you different ratios. So please label your percents. And hopefully they're labeled, but quite often they're not. And I've definitely been thrown for a loop where I thought it was 1% and it was a different one. And I got all my math mixed up because I didn't realize which unit I was using because they're the same unit. They look like the same unit and they weren't properly labeled, which is always frustrating. I do in some cases, is this laziness that it's not labeled, or is it gatekeeping that's not labeled? Because it's effectively doing both. So that's just a point of frustration. Just giving you a heads up. There's also units like parts per million, parts per billion. These are effectively the same thing as percent, but where a percent you move the decimal point over twice because you're timesing it by 100, same thing. These you're multiplying it by a million or a billion. So you're moving your decimal point over 6 times or 9 times because you're dealing with a much smaller ratio kind of thing. So what's going to affect these ratios? And obviously the most obvious one is what are the chemicals involved? And what determines how well chemicals mix together is usually what we call intermolecular forces, or IMFs. And so intermolecular forces are, generally speaking, all going to be electrostatic interactions. Remember, that's what's holding the electrons to the nucleus. That's what's holding your covalent bonds together. That's what's holding your ionic bonds together. By the way, ionic bonds are actually intermolecular forces. So when we're dealing with this one, we could think of the ionic bond, and that's an intermolecular force. You've got one separate ion and another separate ion. They're sticking together because one's a cation, it's positively charged, and one's an anion, and it's negatively charged, and that's going to cause them to stick together, and you're going to get yourself a nice little lattice. That's at one extreme. But maybe it's not a full-on cation or anion. Instead, we could have somebody who's what we call polar. A polar molecule has one end of the molecule is positively charged and one end of the molecule is negatively charged. Now, typically, it's not like a full positive and full negative. If it is, we call those Zwitter ions. They're not uncommon, but they're not all over the place. But instead, quite often, you just have one end of the molecule having a little bit surplus of electrons. Electrons just spend a little bit more time over there, so it gives it a slight negative charge on one end, what we call a partial negative charge. And then you'll have a slight deficit of electrons, not a whole electron worth, but it's just not spending quite as much time on the other end. And so have a partial positive charge, and well, positives and negatives attract and they'll stick to each other, and you can get polar interactions. In extreme cases, usually involving hydrogen, we can get what we call hydrogen bonding, which is very much like an extreme dipole interaction. Alternatively, though, maybe it's not that the atom is arranged such that the electrons kind of spend more time on one side or the other. Instead, it might just be that the electrons at that moment in time just happen to be a little bit more concentrated on one side of the atom or molecule than the other side. And so it creates this dipole where you've got a positive and negative end, but it's very ephemeral. It'll go away in a few moments. And we're talking very short orders of time here. In this case, we call this London dispersion forces. The electrons are kind of dispersed. London is the guy that came up with a lot of this. And so generally speaking, if you've got similar intermolecular forces, they tend to mix well together. Things that are polar, they've got their dipole interactions, or things that are ionic tend to interact together quite well. So polar molecules like water, sucrose, or ionic compounds like sodium chloride, those tend to dissolve in each other very, very nicely. Whereas if you've got mostly London dispersion forces, those will interact very well with each other, something like gasoline, where you have a bunch of nonpolar molecules, but they generally don't interact well with polar molecules. You actually take advantage of this if you're ever creaming sugar for a recipe. So, and I know for some of you this is going to be heresy, but the second ingredient in my cornbread is sugar. So the recipe starts, you take sugar and you pour oil on it and you beat it up, and what you're doing is the two won't mix together. You're going to form effectively a suspension, but in the process of beating it together, the sugar will incorporate air, and that'll make my cornbread a little bit fluffier. I'm then going to put leaveners in there, don't get me wrong. I want a little bit of fluff to my sweet cornbread. Those guys, we have a polar and a nonpolar, they're not going to dissolve particularly well together. This is the classic oil and water. Things that typically dissolve well in water, we typically call that hydrophilic, hydro water, philic lover. And then things that don't dissolve, they're usually nonpolar and they're going to not dissolve in water. We call those hydrophobic, hydro-water phobic furring, even though it's actually the water and the way it interacts with it that's what's preventing them from mixing. Now, that's one thing that's going to control your mixture. Another one is going to be temperature. If we are thinking about our mixture, if we're dispersing it, we're actually increasing the chaos. As we increase chaos, typically that's going to be favored under higher temperatures. So if I'm taking something like a solid or a liquid and I'm dissolving it into a liquid, then it's going to become more chaotic at higher temperatures, or it's going to become more chaotic, and so it's going to be favored by higher temperatures. So, if, hey, I want to make my sugar syrup, I'm going to heat that up to make, my sugar water solution and help get that sugar crammed in there. However, if we are dealing with a gas, it's actually more chaotic as a gas phase. So if you increase the temperature, you're actually going to drive gas out of a liquid. So if I want to degas something, I can boil it, get it to a nice high temperature, and the gas is going to be driven out of it. And you can actually see, the oxygen content of water being affected by temperature fairly dramatically. Actually, as temperature gets hotter, you're going to lose a lot of the oxygen out of the water. This is one reason why you want to chill your sodas. You want to keep that carbon dioxide trapped in there as best as possible. So if you chill it before you open it, then the CO2 won't escape as fast. It's still going to go flat, but it'll stay a little fresher a little bit longer. Also, it just tastes good cold. When it comes to gases, there's also what we call the headspace. So the air or the gas over a liquid, we call that the headspace. And so the more gas of whatever you're trying to dissolve in there is in that headspace, then the more of it's going to be able to dissolve into the liquid. Basically, the gas particles are coming in and out constantly. And the more you have up above the liquid, the more it's going to dissolve into there. So this is how, a soda stream works. You just dump carbon dioxide in there and it's going to cram that into the water. Ideally cold water. It works much better on cold. But also this is how, say, ocean acidification happens. The more carbon dioxide we put into the atmosphere, the more of that will dissolve into the oceans. And it turns out when carbon dioxide dissolves into water, some of it will turn into carbonic acid and acidify the water. So things that can affect the amount of chemicals you can put into your mixture. Well, that is what chemicals are you using? How are they interacting with each other? Your temperature, and if it's a gas, how much gas do you have in the headspace? I will say typically if you've got kind of a limit, so you can only put so much chemical in, we generally describe that as solubility, so how much can you dissolve? If you've got two chemicals, typically we use this with respect to two liquids, but I don't think they have to be two liquids. And you're going to make a solution. You can make any old ratio you want. We say they're miscible. Ethanol and water, we would say those are miscible. You could have pure water, pure ethanol, or anywhere in between the two. Now, let's talk about how we separate mixtures. Typically, we're going to think of in terms of physical means. If you have a suspension, you can just let it settle sometimes. You can put it in a centrifuge and kind of spin it down, so you're basically artificially increasing gravity. It's not actually gravity, it's centrifugal force, but same basic concept. Alternatively, you can filter it. You can send it through a mesh that's got holes that'll let the dispersant through, but will trap the particles that are dispersed into it. So you can do filtering. If you've ever made coffee, congratulations, you've done filtering. At least I sure hope you have. There is a style where you don't filter the coffee. I believe it's the Turkish style. But if you've got a colloid, it's going to go straight through a filter. It's not going to settle out. Centrifuging might be able to, if you really crank up the force, might be able to get you to separate some of your colloid. But generally speaking, that's not going to cut it. So in that case, you're going to need a very thin membrane, or you're going to need a membrane. It's going to have tiny holes, ones that will let the dispersant, which in this case is going to have to be small molecules through, but the colloidal particles will still be too big to cram through there. So this would be something like dialysis or ultracentrifugation. And that's basically you centrifuge, but with a membrane in the process. So it's kind of like filtering and centrifuging combined. If you're a solution, that's a lot harder. You could do something like distillation, where you're going to boil it. And generally speaking, different chemicals are going to have slightly different boiling points. And so as you boil it, you're going to get a mixture of the two chemicals coming off, but you can then let that separate out. And so you can purify it that way. That's how we make distilled alcohols. That's how we make most of our petroleum products. You heat up the crude, either the crude oil or the mash, and then you collect the vapors. And depending on how you do it, you're going to either collect kind of a mixture that's enriched in your more volatile, the one that evaporates better chemical, or if you're able to, in your distillation apparatus, be able to separate out by having a nice long distance and a temperature gradient, you can separate those out. Now, another approach is what we call chromatography. This one's fun to do with the kids. Distillation, a little bit harder because you need heat. But chromatography, this one's actually pretty easy to do, where you're going to have two phases, a stationary phase and a mobile phase. And the stationary phase is, as the name suggests, it's a solid that doesn't move. Technically, it doesn't have to be a solid. There's versions where it's a liquid, but not ones you would be doing in your class. And so the mobile phase moves across the stationary phase or through the stationary phase, and you take a mixture and the mobile phase grabs it and drags it across the stationary phase. And depending on the chemicals in your mixture, some of them will stick to the stationary phase more than the mobile phase. And so those will move slowly, where the ones that staying out more in the mobile phase will move faster, and you're able to separate that out. And it's usually controlled by intermolecular forces. The fun, interesting feature, fun by I mean annoying, is that the easiest one to do is paper chromatography. And you take some kind of water-soluble dye. Chromatography literally means color separator. You don't have to have colors to do this, but it looks nicer if you separate out colors. You put it on like a piece of paper and you let water be your mobile phase. The paper would be the stationary phase. The actual underlying chemistry of paper chromatography is nightmarishly complex. So it's the simplest one to do, but actually explaining that one is quite difficult because you're actually dealing with like water as both your stationary phase and your mobile phase, because the water is being attracted to the cellulose in the paper. And I can't explain it in any good quality other than to say that it is a nightmarishly complex one. But if you just kind of keep it back to stationary versus mobile phase, that keeps it a little bit simpler. It is a nice fun activity to do though. Okay, so let's looking over the focus questions. I think I have hit them all. So with that said, it's probably been a bit. So I'll wrap up this video. I hope you have a wonderful time. If you've never done paper chromatography or coffee filter chromatography, go do that. It is so much fun. Everyone needs to do that at least once in their life. There's directions all over the internet how to do it. And if you're one of my students, it's in your handbook as well. So please go do that. It's so much fun. Otherwise, have a wonderful day, and I will see you in future videos.